Now that we know that a PID controller will drive the steady state error to 0, we can proceed with our design. So for the PID controller, we're going to need to choose its zeros and the gain, which are going to translate into 3 gains when we actually do the implementation. So a nice thing about the PID controller is that we're going to have a non-unique choice of the additional zeros that are going to go into our closed loop system. So it's going to give us flexibility in how the system is going to behave, the input effort's going to require, and how closely we can match the desired behavior of our system. So the choice we make on the zeros, there's going to be an infinite number of them, and then the gain that's associated with those zeros will affect its response. And some designs will get closer to our desired and some will be further away. Some might require much too much control effort, and some might be in an acceptable range. Since we have a selection of zeros that we can choose from, it might be good to start with one that's close to one of our open loop poles. At least we saw a success before that if we cancel one out, that the behavior is going to be more like a second order system. However, we also want to keep in mind that depending on where the zeros are we choose, they may affect our system more or less. So let's start with what's the behavior we want for our output. We desire that the overshoot be 18% or as close as possible, and that the rise time be 0.75 seconds. We're going to proceed that we want these, for whatever reason, to be exact values, or as close as we can get. There might be times where we want the overshoot to be no more than a value, or maybe the peak time, rise time to be less than a value or more than a value. So these could be inequalities, but for this example, we're going to look at equalities. So max overshoot, we know that if we have a second order system, which is what the root locus method is going to be treating our system as, for a second order system, the max overshoot is going to be calculated using only the damping ratio. So we know we want it to be 0.18, and we know how to find it using the damping ratio. The rise time of 0.75, we also know for a second order system how to calculate, and it involves only the natural frequency. So we have two equations for two unknowns. This one is easy enough to solve for. So solving the first equation, this means that our second order system should have a damping ratio of 0.479, and the natural frequency should be 2.4 radians per second. So knowing for our closed loop system what we want the damping ratio and the natural frequency to be, we can compute what the dominant poles are for our closed loop system, because we know for a second order system how the poles are going to relate to the natural frequency and the damping ratio. And we know it's underdamped because our damping ratio is between 0 and 1. Thus, that's why we have this maximum overshoot. So putting in our values for the natural frequency and for the damping ratio, this tells us that we want our desired closed loop poles, the dominant poles, to be located at negative 1.15 plus or minus 2.11 J. Now, there is a little bit of rounding here. I'm only keeping 3 digits of precision. So we, in theory, should get pretty close to the 18% and the 0.75 just based on these dominant poles. Knowing where we want the dominant poles of the closed loop transfer function, now we can go and design what the zeros of our controller should be, and then find the gain so that we can achieve these desired dominant poles. So going back to our system, we have a plant that was provided to us 1 over s plus 2, and we are going to be using the controller for the PID. So when we find our g prime or the root locus transfer function, we are going to take our controller over k times our plant. So we are going to have the controller in the form of s plus z1 times s plus z2 over s. That's from the controller. And then the plant, when we that's the s plus 2 in the denominator. So this g prime has 2 zeros and 2 poles once we have the controller and our plant multiplied together. Just as a side of where we're going, if we expand this out, we are going to find that we actually have these 3 gains, but we're not going to do this step until after the root locus step is done and we find that KD first. We're going to use the KD, the Z1, the Z2 we choose to get those 3 gains. So again, for the root locus, We want to stick with this g prime for right now. We're going to come back to the closed loop transfer function in a little bit, but we'll proceed with this s plus z1, s plus z2 over s times s plus 2. And then again, we're going to see that we can later write it in the form in the middle with a kd, a kp, and a ki. So first thing for this controller, we need to pick the z1 and the z2 so that we can make our root locus and find the kd, and then come back to this. So we have a desired pole that we had a couple of steps ago. So we want to look at this g prime that we formed. Right? So the p values, those are going to come from the poles, are 0 and positive 2. Recall that it's actually the positive values of the poles and the positive values of the zeros, or really the opposite sign of the poles and the zeros, that make the p's and the z's in this step. So since the zeros of this are really at negative z1, negative z2, the z's are z1 and z2. Since the poles are at 0 and negative 2, the p's are at 0 and positive 2. Right, so once again, we want the dominant closed loop poles to be located at negative 1.15 plus or minus 2.11 j. Again, that's coming from the desired rise time and the desired overshoot in the system, which told us what the damping and the natural frequency should be, which then told us that these are where the closed loop poles should be. So we need the total angle of this g prime to sum to 180 or an odd multiple of 180. Right, so remember, with the poles, I'm going to have them be negative. So the first two terms are negative. Those are coming from the p's at 2 and 0. And then I'm going to add the angles from the z's, the z1 and the z2. So again, notice here that in the place of s, I have one of my desired poles. I chose to use negative 1.15 minus 2.11 j. And then, so that's going to be the s in each of these angle calculations. I could have used negative 1.15 plus 2.11 j. That's also okay, but I would use that everywhere in each of these four terms. So the two pole angles, those are negative. So I have a 2 and a 0 that I'm going to be adding to that desired s. And then I'm going to add the two angles from the zeros. So I'm going to add the z1 in the third term and add the z2 in the fourth term. And again, I want that sum to be 180 or some odd multiple of 180. So two of these I can calculate right away because they're just going to be values. So I have the first angle is going to be negative 68.06 degrees, at least to 4 digits of precision. The second angle, I get a negative 118.6. And then the z1 and the z2 I still have to choose. So cleaning this up a little bit, I can get 187 degrees on the left-hand side, and then my unknown terms. So what this tells me is if I move that 187 over, that I am off by 7 degrees, or I'm 7 degrees too high on the left-hand side right now. So I have to select the z1 and z2 such that that total angle will be 180. Or I can express it this way. If I move that 187 over, the sum of these two terms must equal negative 7 degrees. Well, there's one equation, two unknowns. I have a continuum of choices here, so I need to select my z1 and z2 such that this is true. So it's not that any pair of z1 and z2 will work, but there are an infinite number of pairs that do. So I can select the z1 and the z2 in a similar manner to when we looked at the compensators. There was a 0 and a pole we got to choose in that case. So not any combination would work, but there were an infinite number of them that would. So depending on what I select for my z values is going to change the controller, which is going to change the behavior of the system. So I have an infinite number of choices. I'm going to go through two different designs and see how it's going to affect the system.